Now for the final part of this solution, what is called the underdamped. And in the underdamped case, we're going to invert the position of these and define this as being omega. Now you'll recall that what we had just solved was we had a solution where alpha was minus gamma plus or minus the square root of gamma squared minus omega naught squared. So let me rewrite that. Because we know that alpha, this is critically damped. We've already done that. Now we're going to look at underdamped. In the underdamped situation, we have alpha is going to be equal to minus gamma plus or minus the square root of gamma squared minus omega naught squared. But we have, for this underdamped case, we have gamma naught greater than gamma. So we said gamma is less than omega naught. And what we're going to do in this case is we're going to invert the positions and take the square root of minus 1 out. So this is going to be equal to minus gamma plus or minus I, the square root of minus 1, times the square root of omega naught squared minus gamma squared, because this is now going to be a positive number. And we're going to call this number omega. So our response is minus gamma plus or minus I omega. And omega is now defined as this new definition, square root of omega naught squared minus gamma squared. Now what are our solutions? Well, our solutions are, as before, where we take this term here and exponentiate it, and we get these two types of terms. We will get our solution x of t is going to be equal to, we'll write both of these now, a e to the minus gamma t plus I omega t. And then we have another one where we have the other sign. Remember, a second order differential equation has two signs. So it's plus b, another constant, times this other solution, e to the minus gamma t as before. Get a separation there. Minus gamma t as before, minus I omega t. Now I can kind of collect these. I could put a phase in here if I wanted to. That's possible. That wouldn't change anything for any of our calculation, as you know. I'm going to kind of simplify this, leave that phase in, and I'm going to make this constant the same as this constant, and write this as a, and now this is a also. I'm going to pull out e to the minus gamma t, and then I'm going to have e to the plus I omega t plus e, I guess I put the phase there. This would be, actually, this would be plus the phase, and this would be minus the phase, I think. And then over here, we would have e to the minus I omega t. Better, it's probably easier if you just don't see that phase for a moment. Let's wait for a moment before I put it in, and then you'll see where that's coming from. So here we have two terms, and you say, well, these are imaginary numbers. Here I've got an exponential to the square root of minus 1 omega t. I don't know how to make any sense out of this. Well, I've got to give you some review at this point on where these, how to interpret these. You remember your complex numbers. If I have the complex plane, I can talk about a point here, which is x plus I times y. And this would be x, and this would be y, and this would be the real axis, and this would be the imaginary axis, or I, imaginary. And so this number can also be looked at as r in theta, or this is angle theta. And x plus iy, a complex number, can always be written as r e to the I theta. And the important theorem here is that e to the I theta can always be written as the cosine of theta plus I times the sine of theta. This is covered in your mathematical appendix, and if I take this and expand it, you can actually group the terms into the terms without an I and those with an I, and those without an I turn out to be exactly the terms that make up the cosine of theta, and those with an I make up the sine of theta. Just for a little bit of practice, let me review that. That would say e to the I theta is equal to 1 plus I theta plus I squared theta squared over 2 factorial plus I cubed 3 factorial theta cubed plus I to the 4th over 4 factorial theta to the 4th. That's what the exponential means. So if I group the real terms, I squared is minus 1. So this is 1 plus a minus 1, a minus theta squared over 2 factorial. And over here, that's a minus 1 squared. I to the 4th power is 1. So it's plus theta to the 4th over 4 factorial. Theta to the, I've already got the theta to the 4th, and then other terms. That's the real part. Then the imaginary part would be plus I times theta. And this is I cubed, so it's a minus sign times I, minus I theta cubed over 3 factorial, plus this will be theta to the 5th over 5 factorial, and so forth. This term, this expansion here is exactly the expansion for cosine of theta. This one is the expansion for sine of theta. Those are real important. It's important that you remember what those expansions are. That e to a power is always, e to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. That's what that symbol means. An exponential means that, e to that power. And a cosine means 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. All of the even powers, and therefore cosine is an even function. Here, the sine of theta is going to be theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so forth. So now, where does that lead us? It takes us back into knowing how to take these two terms here and write the solution x of t is equal to a e to the minus gamma t, and we'll leave the phase out for the moment, times, if I take the sum of this and the one with the negative, you'll notice that I end up with a cosine theta plus I sine theta, cosine theta plus I sine theta. And also then, for this term, I end up with cosine theta minus I sine theta. Why? Because this has a minus I where this one has a plus I. Therefore, I got a minus sign here, and you'll notice that out of these two terms, the imaginary part will now cancel. And I end up with a times 2 e to the minus gamma t cosine theta. Now, if I'd had the phase with me, there'd be cosine theta plus delta. And we know what this theta is. This theta is going to be equal to this term omega, because we've compressed this down. This is the omega times t here. So this is actually omega t plus delta. So what does our solution end up being? For the underdamped case, that's where the gamma is less than omega naught. We inverted these, got an imaginary number, and we're able to solve this. And we end up with x of t is equal to, and now I can just change this and define, a can be anything, so I define a new a to be that old a. We can call it anything, a prime, e to the minus gamma t cosine of omega t plus delta. This is a very important result because it's a fast and easy way to solve using imaginary numbers for very, very difficult types of differential equation. And we end up with this where I have an exponentially damped solution times an oscillation. And what is that going to look like? See, again, the sun's coming in here. That's going to look like the following. If I have an exponential damp like this, it multiplies the cosine. The cosine will oscillate between these two like this. And that's what this solution looks like. Starting out at a magnitude of A, and again having omega, which is the oscillation given by the square root of omega naught squared minus gamma squared, which you could calculate, and some phase possibly, if the phase were different. And so this is like you go through the saloon door and it goes flop, 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 dying out as we go. Or a mass that's on the end of a spring, oscillating, but the dampening makes it smaller and smaller. Or equivalently, a pendulum, as we can show later, a pendulum where the pendulum's swinging back and forth, but it gets less and less and less due to friction because there's no other applied force.